Hello, and welcome back to the course on Physics for Engineers. So this is now the last lesson for this chapter, the chapter on electromagnetism. So before we proceed with this last lesson, let us first review some concepts. So in the previous lessons, we have discussed about Gauss law for electric field and Gauss law for magnetic fields or magnetism. We also have discussed about Ampere's law when we discuss about an alternative to law of Biot-Savart. And lastly, in this chapter rather, we have discussed about Faraday's law. So for this last lesson, it's basically just a generalization of this chapter and the past chapter on electrostatics and magnetostatics. And we will be basically lumping together all of these equations and call them Maxwell's equations. So Maxwell's equations for electromagnetism is basically a collection of equations which gives you a comprehensive description of the classical electromagnetism. So this is composed of Gauss law for electrostatics. The closed integral of E dot dA is just equal to the charge enclosed over epsilon naught. Gauss law for magnetism or magnetostatics, which is just the flux. Basically, this is the flux, no? The electric flux. This is the total electric flux. This is the total magnetic flux. So in magnetism, since it's always a dipole, then the total magnetic flux is always zero. That's the Gauss law for magnetostatics. Then we have Ampere's law, B dot dL is equal to mu naught I enclosed, an alternative to the law of Biot-Savart. And lastly, we have the Faraday's law, which is E dot dL is equal to a negative time rate of change of magnetic flux. So this is the induced EMF. So if you will notice the pattern, it's E dot dA, B dot dA, B dot dL, and E dot dL. And all of these four equations are called Maxwell's equation for electromagnetism. So if you'll notice, it's actually not Maxwell who originally made or formulated these equations or these theories, but he was the one who collected all of these four and comprehensively described what is an electromagnetic field. So basically, this is very significant since most interactions in nature are electromagnetic. So when you touch something, it's basically just an interaction. The touch sensation that you feel is basically just the interaction between the electric charges in your finger, at the tip of your finger, at the atoms or molecules of your finger, and the tip or the atoms or molecules, the charges in this case, in this cactus here. So that's still electromagnetic. So when you taste something, same principle, you're basically just an electromagnetic interaction between the particles, in this case, between your tongue and the particles in your strawberry. So that's still an electromagnetic interaction. Now, when you see things, that is still electromagnetism. Why? It's because light, when you see light is actually an electromagnetic wave. So this is now how we relate the chapter on electromagnetism to the last chapter of this course, which is on optics. Optics is a study of light, and light is an electromagnetic wave. So basically, if you have an electromagnetic field, and that field is actually changing, that field is actually waving, so you will actually see light. But actually, we only see a very small fraction of the electromagnetic light spectrum. We only see visible light. We don't actually see Bluetooth. We don't see Wi-Fi. Those are still light, electromagnetic waves. But we don't see them. We don't see infrared. We don't see ultraviolet light. So those are things that we cannot see, which are only limited by we are limited by our eyes, but still those are electromagnetic waves. So that is the relationship between electromagnetism and the last topic for this course, which is on optics. So that is how we relate the chapter on electromagnetism and electromagnetic field, and basically the last chapter, which is optics, which is all about light. So light is an electromagnetic wave. And I will see you again in the last chapter of this course, which is all about light, which is all about optics. So bye for now.